Welcome to Online Algebra 2, and this is section 5-7, the binomial theorem. So our objective here is to expand a binomial using Pascal's triangle and to use the binomial theorem. Now what you should know is that you can use a pattern of coefficients and the pattern of, a to the n, n minus 1, b, a to the n minus 2, b2, so as the exponent of a goes down and the exponent of b goes up, we can use this pattern to write an expansion of a plus b to the nth power, a binomial expansion. Okay? So, we could, if we wanted to, take a plus b to the third and expand it using the distributive property. That just means we're going to take a plus b and we're going to multiply it together 3 times. And the way you would do it, right, would be a plus b times a plus b. We would FOIL this together and you would get a squared plus 2ab plus b squared, and then you would take that whole thing and now multiply it by a plus b for the third time, right? And then you would distribute each term, and you would finally wind up with this expression right there. Okay? That is great. That will always work, but could take a while, right? Third power is not so bad, but what if we wanted to do something like that to the 7th power? Okay? I don't really want to multiply a plus b 7 times. That would take a long time. So I'd rather have some sort of shortcut that could help me. So if we look at a pattern here, okay, and we take a plus b to the 0 power, anything to the 0 power is 1. Then we take it to the 1st power, it means we don't really have to do anything. Notice this pattern is that we have these 1s here, and the exponents are both 1, so not a lot to get them that. We know what these two are because we just did both of them. A squared, ab, b squared, 1, 2, 1. So notice that the exponents for a are going down until they go away, and the exponents for b start at 0 and then go up. And same thing happens with the cubic expression. And finally, if we look at something to the 4th power, we can see that this pattern keeps going. 4, 3, 2, 1, and 0 for a. B goes up, and then we have these numbers right here in the front. Okay? And if we just look at the numbers in the front, the coefficient, we have this triangular array of numbers. Okay? And this coefficients only column, right? This triangular array right here is something called Pascal's triangle. Okay? And this is named after Blaise Pascal. It is a triangular array of numbers in which the first and last number of each row is a 1, and each of the other numbers is the sum of the 2 numbers above it. So let's get Pascal's triangle. Okay, I'm going to show you how easy this is to do, and you can do it anytime you need it. So I start with a 1. Then I start with 2 1s in the 2nd row. The next row of Pascal's triangle always starts with a 1. It always finishes with the 1. And you put the 1 to the outside. And the middle numbers here you get by adding the 2 numbers above it. So 1 and 1 give you 2. And then we finish with a 1 on the outside. Okay? So I start with a 1, add these 2 to get a 3, add these 2 to get a 3, and then I finish with a 1. 1, 4, 6, 4, 1 for row number 4. Add these 2, 10. Add these 2, 10. Add these 2, 5 and 1. And you can keep this going as long as you needed to. Okay? And here it is, nice and written out, row 1 to 8. Okay? And the way you get, right, the way you get 5 is you add 1 and 4. The way you get 10 is you add 4 and 6. Now, this is row 0. Okay? The row number can be found by looking at the second term. Okay, so this is row 1, so this is row 1, 2, 3, 4, right, row 8 down there. If I wanted to make row 9, start with a 1 and I add these two together. Okay, then I add the 28 and the 8. Okay, 36. 28 plus the 56 gives me 84. 56 and the 70 give me 126. And notice that they either have a middle or they repeat each other, and the left side is going to be the same as the right side. So this is going to be 126 again, 84, 36, 9, and 1. Okay? And again, so we can keep this going as long as we want to. Pascal's triangle. So how is Pascal's triangle going to help us expand a binomial? Well, let's see. What is the expansion of a plus b to the 6th power? Again, I don't want to multiply a plus b 6 times. So what I'm going to start with is the 6th row of Pascal's triangle. Looking back, row 6 is that one right there. Okay? And the way I like to do this is I like to do this vertically. So 1, 6, 15, 20, 15, 6, 1. Right from right there. Okay. Now, that is the first term. A. I start it with the maximum exponent. Then, as I go down the column here, my exponent goes down by 1. A to the 5th, a to the 4th, a to the 3rd, a squared, a to the 1st, a to the 0. Anything to 0 power is 1, it just goes away, and I don't need to write a first power. Okay, this is the second term. It does the opposite. Instead of starting at 6 and going down, it starts at 0 and goes up. Then we do any calculation we need for each term, and we put all these different terms of the polynomial together. So a plus b to the 6th power would be a to the 6th, this one, plus 6 a to the 5th b, 15 a to the 4th b squared, plus 20 a to the 3rd b, whoops, a to the 3rd b to the 3rd, 15 a squared b to the 4th, 6 ab to the 5th, and b to the 6th. Okay? That would have taken me way longer if I took a plus b and raised it to the 6th power. Okay? If I wanted to do something to the 8th power, I could. All I have to do now is use the 8th row of Pascal's triangle, which is 1, 8, 28, 56. And it's tough to get this without drawing out the whole triangle. Okay, so I just flip back to the other page where I have it, and I'm just copying it down. 56, 28, 8, 1. And if you ever have a question where you need to use Pascal's triangle, it's pretty easy to make, right? 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Just keep going until you get the row that you need. Okay? So this would be 8, 7, 6, 5, a to the 4th, 3, 2, 1, and then 0. And then the next row would start with b with 0, b squared, b to the 3rd, b to the 4th, to the 5th, to the 6th, to the 7th, and then b to the 8th. And then we just add all these different terms together to get my polynomial. Now, The way the binomial theorem works is it just gives us a general formula for expanding any binomial instead of just two variables. So we take the coefficients of Pascal's triangle in the nth row of Pascal's triangle, and we do just like we did with the previous problem. We start with a to the nth power. A goes down by 1 exponent each time. B goes up by 1 each time. Now, the thing to be careful is here A is x, B is -2. Here A is 3x, and if we're going to raise it to any power, right, 3x to the fourth, right, if we're looking at the fourth term, is not 3x to the fourth power, okay? It is 81 x to the fourth power, 3 to the fourth and x to the fourth. Remember, you must raise both of those terms to the fourth power. So that is the easiest place to make a mistake and what you need to be most careful of. So let's try to expand that expression. 3x minus 2 to the fifth power. In order to do this, you need the fifth row of the binomial or Pascal's triangle. If you don't remember it, just make Pascal's triangle again. 1, 5, 10, 10, 5, 1. So that's what I'm looking for right there. So I go 1, 5, 10, 10, 5, 1. Okay, we'll get rid of this. And this is now my first term. It gets raised to the fifth power, fourth, third, squared, first power, and then nothing. This, the -2, is now my second term. First power, squared, third, fourth, fifth. Now, the last step here is we actually have to calculate all the different parts of this expression. So 1 times, remember exponents first, doesn't matter because it's 1 anyway, so nothing really happens there. 3x to the fifth, 3 to the fifth power is 243. So it's 243x to the fifth. Exponents come before multiplication. Don't forget order of operations. 3 to the fourth is 81 times 5 times -2 is a -810 x to the fourth. Okay, so first term was positive. Okay, second term was negative. Watch what happens to the third term, because -2 squared becomes a +4. So that's 10 times 3 to the third, which is 27, times a +4 is a positive 1080 x to the third, because we have a third power here. -2 times -2 times -2 is -8 times 3 squared is 9 times 10 is -720, and 2 times 2 times 2 times 2 is 16, and no exponents here, so 16 times 15 is a positive 240x, and finally 2 to the -2 to the fifth power is a -32. So my only variable here was an x. You can see that it's going down by 1 term each time. My negative sign here in the second term made the expression change signs each time, because odd exponents stays negative, even exponents, it cancels out the negative sign. Okay? And the rest is just using Pascal's triangle to fill in the coefficients and to be sure that we just be careful when we multiply. Right? Let's set up this one right here. 2x minus 3 to the fourth power. So that would be 1, 4, 6, 4, 1. That is the fourth row of Pascal's triangle. 2x to the fourth, 2x to the third, squared, and then nothing. And then negative 3 starts at nothing, first power, second power, third power, fourth power. So 2 to the fourth is 16. 2 to the third would be minus 96x to the third. So then we have a positive 9 times 6 times 2 squared is 4 plus 216 x squared. Second to last term is a negative 27 times 2 times 4. So that is a negative 216x. And then positive 3, negative 3 to the fourth power is 81. Okay. Weird thing that happens, right? Look at the different powers of 11, and you can see that they sort of mirror the coefficient matrix in the Pascal's triangle. Weird thing that happens, it doesn't actually keep working. So it doesn't actually, 11 to the fifth power is not 1, 5, 10, 10, 5, 1, because now we have, some tens in there, so that really messes up. You got to put one more into the next digit over. So it would work, but it doesn't come out quite as cleanly as the rest of them do. But kind of a cool little thing that happens when you raise 11 to a power. Let's try one more with some variables, 2 variables, and an exponent inside. So fourth power, fourth row of Pascal's triangle. We take 2u, raise that to the fourth, 2u to the third, 2u squared, 2u, and then nothing. Now, we start with nothing with the second term, 4v to the third to the first, 4v to the third squared, 4v to the third, and then 4v to the third to the fourth. So what's going to wind up happening here, for the first term, it's not going to be anything too crazy. It's just going to be 16u, that's the u, 16u to the fourth. But for the second, even for this one, it's not too bad. We still do the exponents first. So that's 2 to the third is 8 times the 4 and a 4. So that's 128. We got 3 u's, u to the third, and this v to the third there. Okay, so the u is going down by 1, but the v is going up by 3. Okay, next one. 6 times 4 times 4v to the third squared. So the 4 gets squared, which is a 16. So we have a positive 384 u squared, power to a power, multiply the exponents together. Okay? 4 to the third times 2 times 4 gives me 512 u v power to a power. You multiply the exponents, and then the last term, 4 to the fourth power, would be 256 v to the power to a power, multiply the exponents together. Couldn't fit it over on the other side there. But notice that the u goes down by 1 term. The v's go up by 3, 6, 9, 12. Okay? And then 4 times 3 gives you the 12. That was section 5-7 the binomial theorem.